Greetings, friends. We're going to start this last week of instruction with one more Faraday example, and then we're going to roll into characteristics of the inductor as a circuit element. And we'll talk a little bit about DC. I'll review a little bit about the DC capacitance, and we'll do some DC inductance. And then we'll get at least 2 days worth on AC circuits. So that will finish us up for the end of the semester here. Alrighty, well, let's get started, I suppose, with an example on Faraday's law. And it's kind of an interesting one. I'm going to do this one for a particular reason. And I'll show you that reason as we go along. So this is called the betatron. It is a particle accelerator. And what it does is it accelerates electrons and it moves them around in a circle and increasing speed. And how does it do? And by the way, why is it called the betatron? It's because the electron also goes by the name of the beta particle. So it's the electron. It's really an electrontron. You can't call it electrontron, I suppose. Well, I guess you could. So what I want to do this example for is to show you that we've been talking about Faraday's law as existing with loops of wire and the voltages that are induced to them on the loops of wire. So what I want to do this time is to talk about a magnetic field here. Let's see if I can do this. A magnetic field which is 1, 2, 3, 4, 5, 6, 7. A magnetic field which is it's not a constant field. Well, it is a constant field, I suppose. It's just not well, it's an axially symmetric field, I guess. 1, 2, 3, 4, 5, 6, 7. Let's see, that should probably be enough. Let's go for this one. Okay, so here's a B field. And I'm going to draw it as if we're looking kind of this is the top view of it. Of course, it's coming out of the page, which is why all the dots are here. Okay, so that's B. And so what happens is in a betatron, you get electrons orbiting around in circles. So we're gonna get an electron orbit here. Suppose it looks something like this. Okay, so here's my electron orbit, and it's circulating around, but we don't know which way. Okay, so let's try and find out what we're going to do to figure this out. So from the side view, so this is the top view. Now, if I draw the side view over here, maybe I can fit it all on one page. Suppose I do something like this. Okay, so the side view, what I'm going to do is basically imagine that dotted line is the plane of this red circular electron orbit. Okay, and this is what the B field looks like in this. I'm gonna have to. This is what the B field looks like. always coming out of the page, so it's going this way. All right. But you'll notice that on that surface, the field is always pointing up. The tangent field is pointing directly straight up. Okay, so that's why the dots, that's why I drew the dots the way I did, because right in this plane of the field is tangent upwards, even though it's going to eventually do other things after that. So let's suppose that the B field is, so it's varying spatially, as you can see, but it's symmetric on both sides, right? So if I choose that middle, if I choose this middle arrow and I look to the left and I look to the right, on my side view over here, then it looks essentially like if I folded it this way, it looks actually symmetric. Okay, and let's have the B field increase with time. Okay. So that means that we're going to have a varying B field through the electron orbit. Okay, so let's take a look at the electron orbit. So if I have a circle going around here, and I had injected an electron going at some speed v, and it's making this orbit. So which direction, because I know the magnetic field's coming out of the page. So what direction would I need the electron to be circulating in order for this electron to be making well, which direction should the electron be circulating based on the direction of this magnetic field? That's the question. And we're going to go back and think about the magnetic force, which is a QVB force, right? So the velocity is tangent. The velocity is tangent to the path, so the electron makes. And so we got to use our right hands to try and figure out which direction the velocity is going to be, because we know the direction of the field and we know the direction of the force, right? The force has to be centripetal. So if you think of a radius, here's a radius of the circle. It's maybe about right there. Okay, so there's your radius r. So we know that when the particle's over here, the force of the B field has to be centripetal. Okay, so if we take our right hands and we say, okay, and remember this is an electron, it's a negative charge. Okay, so if we go, say, well, it's easy for me to just kind of align my right hand this way. So if I go V cross B, B would be out of the page. That would give me a force which is out. Okay, so I have one of two choices here. I say, okay, well, for a negative charge, that would have made, for a positive charge, the force would be this way. If it's a negative charge, the force would be that way, which is what I want. Okay, so the V that I chose must be kind of going around counterclockwise. The other choice you can say is, look, I've got the V of a positive charge going this way, curl with the field gives me a thumb pointing outwards, right? So that would mean that if I had thought of my velocity, right? My velocity of positive charges is going that way, it's going circulating counterclockwise. If I go with that positive velocity, that's like a negative velocity, it's like a negative charge velocity going the other way. Okay, so I could say, oh well, a negative charge going clockwise is the same as a positive charge going counterclockwise. Okay, so if I had a negative charge going clockwise, what I would have gotten is align your fingers with the positive velocity, positive charge velocity, curl and get this. So if my negative charge was circulating clockwise, it would be pushed away. So it wouldn't be circulating. Okay. So this one has to be opposite. I guess that's what I'm ultimately getting at here. The velocity of the negative charge right at that point, velocity of an electron would have to be that way. Okay. In order for the force to be inwards. Okay. So I don't usually do this, but you could also, there's one other way to do this, and that is, since I've heard some of you talking about it, I'll address it. That's also because the positive charges obey the right hand rule, and the negative charges obey the left hand rule. Okay, so you can also see if this is a negatively circulating charge, you could do that. You could go VB out in like that. That was off the record, and you can just pretend I never said that. But if you're one of those people, then you can do that too. Okay, so we know the direction of the orbit of the electron. It's going counterclockwise. And what we're going to do is increase the magnetic field in the, well, we're going to increase the magnitude of the magnetic field. Okay. So we've got a varying B field. I mean, like a varying with time is what I mean with this. So that means we've got Faraday's law to think about. Okay. Now, Faraday's law, what we've been talking about is, the voltage. We've been talking about the voltage induced, and we've talked about the EMF, and that's with a current loop, right? With an actual loop of wire. Okay. Notice there is no loop of wire here. Okay. There's no wire. There's no nothing. It's just space. There's a magnetic field and there's space. Okay. And what we've done is we managed to put an electron in there that's circulating at some velocity. Okay. Just a minute. Okay. No time has passed for you, so this is good. Back to this. So the B field varying with time, if you recall, the Faraday law from the Maxwell equations, then they didn't have a voltage in them, right? So my point was, we've been talking about a voltage because and currents induced because of the wire that has been, the coil of wire that has been there to catch the flux change through its area and stuff like that. But what, as with many parts of this class before, what if the loop wasn't there? We took it away. Well, there'd be a voltage induced in nothing, okay, in space. Okay, you could, yes, there will be, because excuse me. If you recall the Faraday law from the Maxwell equations, it doesn't mention anything about voltage. It says that the circulation of the E field around a curve is d by dt of the flux of B through that curve, through the surface, right? Through surface S. The surface S, which is bounded by curve C. Okay, so this is a circulating E field. Well, it's not literally circulating with time. It's got a circulation to it. It's got a curl to it, if you like. The right-hand side of this we've been dealing with, right? The flux of the B field, the time rate of change, and we've been talking about that as the inducing of a voltage. But look at the left side. That E dot ds really is kind of a voltage, except now we've got a loop to go around, right? Now it's got to be around a closed loop. It can't just be E dot ds through space, like from infinity to point P or something like that along a straight line. That's not technically, I mean, that's not what this is, right? This is start here, circulate all the way back around and come back to your original point. Okay. So what's happening here, if we go back to the picture, is that there's an electric field, okay, and we increase, so remember, we're increasing the B field with time. We're starting low and making it stronger, okay? We're not changing its distribution. We're not changing the spatial distribution. We're just kind of starting it low and then making it stronger. As we do that, which way, what's going to happen to this electron, essentially, okay? What's going to happen to the electron orbit? So you take a look at this and you say, okay, well, there's flux. If we just do a bit of qualitative reasoning here, there's flux through the loop of the electron orbit. Okay, remember, there's no actual wire here. It's just an electron going around a path. Okay, so the flux of B field through that loop is increasing. Okay, what Faraday's, oops, I can get it on one page. So what Faraday is telling us here is that if we look at the time rate of change of that and then flip it around, right, and flip the direction. So if I have an increasing B field, it's increasing out of the page towards me. So the time rate of change is out of the page towards me, and therefore negative is into the page, okay? It's just as if you were speeding up or slowing down. If you have an acceleration which is in the direction of the velocity, that's speeding up. And if you're slowing down, you have your acceleration opposite the velocity, right? So this is just going opposite. So the B field is out of the page. It's increasing, so its rate of change is also out of the page because it's getting stronger. So negative that would be into the page. And that's going to induce an E dot ds, a circulating E field around that loop, okay? Now, I want to just make sure you understand, this is a loop that I just picked, and this is going to happen with any loop that you just pick, okay? It's not just because I have this one and therefore this is the only one where an E field is going to be induced. No, it's going to be induced around any loop that you pick in space, any of them, all right? As long as there's B field that's increasing or changing with time through that loop, then there will be an E field generated around that loop, okay? So if I use the right-hand rule, and I'm going to go, okay, so I'm going to take the negative flux direction, negative change of the flux direction, negative of the flux direction change, that's into the page. And my right hand should tell me if I go into the page and I circulate with my fingers, that's the direction of the circulating E field. So in this case, the E field is circulating clockwise. Yes? So E field is, maybe I can change, let's see, I've got that, I should change to something like a blue here. So the E field is because of the increasing flux, the E field is circulating. I had that, so I'm going to draw it like this. It's right. This is a circulating E field. Okay. I don't mean for these arrows to be different lengths meaningfully. I just started small and for some reason got a bit larger with them. Okay. So that's the circulating E field. Okay. It's opposite the direction of the increasing flux change, right? Flux is increasing out of the page, go into the page, opposite that, and then twirl your fingers, and that's the direction of the E field. So the electron is circulating counterclockwise, and the electric field is directed in a circle around that exact circle clockwise. What is happening to the electron? question, what is happening to the electron? Pause, answer the question. Okay, what's happening to the electron is that it must be feeling a force due to the electric field. The electric field is exerting a force on it, which is, as the Lorentz law would tell us, negative E, negative little e times capital E for the electric field. So the force on this charge, due to the magnetic field, is inwards, okay, and it pulls it around in a circle. The force on this charge due to the electric field is tangent and is that way. Force due to E, right, is that way. And it consequently speeds it up. Okay, so this is the acceleration, the tangential acceleration. It's already radially accelerating, right? So it's tangential acceleration due to the electric field. Okay. So note that the electric field then does work on the charge in order to increase its kinetic energy. Okay, so let's try and go from there. If I take a look now at this E dot ds, the circulating E field, around the loop, it has a constant value, magnitude, right? And E dot ds, if I circulate with the loop, the dot product is 1 because the electric field is always tangent to the loop. Okay, so this really turns into our good old field times 2 pi r for the radius, for the circumference of the circle. Okay, so that's my path around the circle with the dot product becoming 1 and the E field being constant on that loop. Now I choose a different loop, I might get a different E, right? But on this one, I'm getting this value. So I've got to set that equal to the time rate of change, the negative time rate of change of the B dot dA. Well, we've already got the directions figured out, okay? So the negative is no longer important. We've already figured out what's happening. So I'm going to drop the minus and just go with magnitudes, okay? That's all the minus is, as you know. By this time in your physics career, I hope you know that minuses are just about direction, okay? So if you figure the direction out, you put that off on one side, and then you do the calculation, and then you say, ah, yes, it was in this way. Okay. Otherwise, having the negative in there kind of louses things up, as you found out from Coulomb's rule. Okay, so what about this negative time rate of change of B dot dA? So we're going to, in order to really do this integration, this flux integral, okay, go back up to the picture here. In order to really do this flux integration, I would need to know what the function of the field was in space in order to do this and say, oh, okay, so is it increasing R with R, or is it what's it doing with this and that? Because that is not the focus of this problem, this example is about helping you think about the electric field that is present and has a curly nature to it whenever the flux of the B field is changing. That's the point. That's the point of this problem, right? Normally what we do is we just put a loop of wire right there and say, in the wire, this electric field's driving charge. Right? So because this flux integral is not the point of this problem, I'm just going to say there's some average field inside the orbit, okay? And I'm also concentrating on the magnitude only. So I'm just going to drop the minus sign. Why? Okay, magnitude. So I'm dropping the minus sign. I'm going to get d by dt, and I'm going to have I'm just going to call this an average B. There's an average B inside here, okay? I don't want to go through the whole thing about trying to figure out what the function of the B field is through here. Okay, so we need the time rate of change of that. So this gets in this derivative gets into the parentheses here, and it says, okay, which one of you is time rate of changing? And well, it's going to be the B field, right? So this ends up as pi r squared times dB average dt, and that should be equal to E times 2 pi r. Okay, so if I just flop the the R and the pi is gone and there's a 2. So this gives you the size of the electric field that is induced, okay, which is 1/2 R. This is the size of the electric field that's induced by the flux change of the magnetic field, okay? This is the magnitude of the circulating E field. We already know its direction. It's tangent and clockwise, right? So we can include that. It's clockwise. And it's only there when dB dt is not 0. Okay. So here's a little bit of interestingness. So what's the effect here? If you increase the magnetic field, then you get the electric field kicking up and causing your charge to accelerate. To tangentially accelerate, right? To speed up. So let's check and see if we can find out what happens. What is the force on the charge? The force on the electron must be, right? QE, this is the part of the Lorentz law that we talked about, and this is minus E times capital E, which tells you that for negative charges, the force is opposite the electric field, okay? Okay, well, and we now know the size of the electric field, okay? And I can take this minus and throw it away because I know the directions, okay? So I know what this electric field is, it's that. But what is the force? Well, Newton's second tells us that the effect of the force is to time rate change the momentum of the thing. So if we do this, now this is equal to 1/2 ER dB average dt. Okay, so if I put that E field in there, the time rate of change of the momentum is equal to this thing. If I want to find out what the momentum is doing, I'm going to split this derivative up. And I'm going to put the dt over here and integrate the momentum. Okay, so I'm going to change this into something that I can integrate on both sides. So on the left, I'm going to do dp, and the acceleration, the electron is going to go from some initial momentum to some final momentum. And I'm going to put the dt on the other side and integrate this side from a I don't know, a T naught to T1 or something like that. 1/2 ER, and then there's a dB average dt, which I'm integrating dt. Well, whenever you integrate a derivative, it goes away. So this thing on the right really becomes just a magnetic field integral. So if I take those dt's away, and my screen can move, there it goes, finally. Okay, so this thing really becomes not a time integral anymore. Now it becomes a magnetic field integral. 1/2 ER dB average. So the momentum, oh man. So the momentum of this thing, as it goes from P0 and increases in momentum to P1. Okay, we're back. Good. It's going to be P1 minus P0 equal to 1/2 ER average minus B1 average, right? Average. Right. So in other words, the momentum, the linear momentum of the thing has increased. At some rate due to the magnetic field increase. Okay. Pretty cool, right? So you're increasing the momentum of the particle by varying the magnetic field. And if you get back to a question I kind of dropped in there a while back about the magnetic field not doing work, this is pretty much how it gets away with that. The magnetic field doesn't do any work here, but as you increase the size of the magnetic field, all of a sudden the particle speeds up, which means there must have been work done because the kinetic energy is now higher if the particle speed up, right? So then you ask, well, how can the magnetic field do no work if I increase the size of the magnetic field and the particle speeds up? Well, technically, this is the subtle way that the magnetic field does no work. It actually tells the electric field to do the work. Yes, you can kind of see that the electric field that's induced around the loop is pushing the charge. It's not the magnetic field that's pushing the charge, it's the magnetic field that's inducing the electric field. So the electric field is simply doing the magnetic field's bidding. The magnetic field is the boss. That's why it's called the B field. It's the boss field, because it's going to tell the electric field, hey, get that thing and get it moving, right? But I'm not going to do any work, but you go take care of that, right? It's the boss field. Okay, so that's all I really wanted to show you. So the rest of this was just a bit of funsies with the momentum and stuff like that. Don't worry about that. The point of this was to just make your, kind of get back to the roots of what Faraday's law is telling us, that there's an E field induced and it's around any loop. We just happen, in all of our time up to this point, we just happen to have been putting a coil of wire there so that current could be pushed by the electric field that is circulating in space right at that point due to the flux change of the B field. Okay. So I just wanted to do an example which kind of reinforced that and reminded us that really this is what's going on. Okay. Okay. So, that is pretty much what I think I have to say about Faraday's law, and let's move on to some induction. Um, Actually, let's stop and I'll do induction in a separate video. That's what I'll do. So next video I want to do is going to be on the DC responsive inductors, and we'll review the DC responsive capacitors, kind of the same one that you found from your capacitor investigations. So that will be our next video, and then we are going to, so that kind of introduces the inductor as a circuit element, and then we're going to look at the inductor in a DC setting, and then we're going to move into an AC setting now that we have both the capacitor and the inductor involved. All right, so good. Hope everything's going well, and we'll talk to you soon.